Alright, so we are going to talk about transformation of quadratic functions. I do have y equals a times x minus h squared plus k. Since these are functions, I am just going to change this to f of x. Realistically, though, for the purpose of this transformations, it could be functions or equations. Technically, even an expression just for the idea. And you should just remember that f of x really just means y, which means that it's just a fancy way to restate that the word, this is the output that we're looking for. So let's just define the letters of what we have here. And in fact, I'm actually going to change it to y because that will maybe make our lives a little bit easier. So let's just talk about it. So we should see some things that are pretty obvious. We see an x and a y. This is just an ordered pair within this equation, okay? And so if we kind of sketch it, and I put kind of this sketch here of a curve, right? This is just a sketch of a quadratic curve. We know the equation, we'll call it the parent function. So we have the origin of 0, 0 is a vertex, which is hk. So by now you should have learned how to identify a vertex, but maybe not exactly how to calculate specifically a vertex, but in vertex form, the values in the position are the vertex, and so this is just the vertex, and there's just the letters used to describe it. Now the letter h in this problem is also the value of the axis, we'll call it the axis of symmetry. Right? That is, and it results in x equals h. So we can write the equation for the axis of symmetry as x equals h. So there's a lot we can do in this structure, but these are what everything mean. And then of course the a value is what we call a dilation. So it will make your graph two effects. It'll make it wider or narrower. Now we have better language to describe that, and we'll get more accurate with it, but we often call this a stretch and this a compression, but we do have to be careful of how we kind of look at it. And then A also can result in a reflection when the value of A, if A is negative. Okay. Now, I presented vertex form in a very specific way because this is how it's presented. So, what does each of the things do? Well, more specifically, hk is the vertex. So, h has a very specific effect. It is a horizontal shift, which they call translation. So we'll use the word translation just to write it, but it means to shift or slide. Okay, so it's just sliding it back and forth. So this goes side to side. So we see the effects side to side, where k is a vertical shift. Okay. Or translation, really, which means we move it up or down. Okay, so these are kind of the effects. We're going to come back to this, and we're going to kind of look at some stuff on the graph. So here we see the format with just the parentheses. So as soon as you see parentheses, whatever is in the parentheses tells us we are shifting one way or the other. So I have these two situations above, here and here, where I have this x minus h squared and this x minus h squared. They're both in different colors, but why are they in different colors? Well, the parent function is just y equals x squared. This one is to the right 3 units. Each of these units, like this unit went 3 units to the right, this went 3 units to the right, this went 3 units to the right. So the whole parabola on this situation was shifted 3 units to the right. So I would just plug in 3 here. So this is going to look like x minus 3 squared. So if I'm looking to the right, it's just x minus h, right? And if I'm going to the left, I went in 1, 2, 3 units, so I'm plugging in -3 here, which means I plugged in a negative sign inside that box. So that's a little tricky, but what happens when you subtract a negative? This becomes x plus 3 squared. So x plus 3 squared is to the left, x minus 3 squared is to the right. So we can conclude that if I'm going to the left, it's x plus h squared. If I'm going to the right, it's x minus h squared, because the values that I plug into the formula can change the sign or keep the sign, since the sign starts out as subtraction. That's not really the same effect on k. K is just a vertical movement, so we are either going up or down. And so it's plus whatever or minus whatever. Since this is a plus sign for the value, if I plug in a minus, it's going to just keep it as a minus. And we'll see that as if I plug in 1, 2, 3, that means I went up 3 units. So this graph here is just x squared plus 3. Here I went down 1, 2, 3, 4 units, so I'd put a -4 in here. So we're not going to write plus negative, so we're going to write x squared minus 4. Alright? Although it's x squared plus k, when I plug in the -4 for k, it's just going to be left as x squared minus 4. So kind of easy to navigate. And then we have an example here. So we have some that are dropping below, but we have this graph. Again, here is the parent function, and then we have this function here in green. And we're going to kind of look at how we got from this ordered pair origin, right, which is 0, 0. This value here is over 1, 2, 3, 4, down 1, 2, 3. So the vertex on this is -4, -3. So I can literally plug those numbers in here and here, since this is h and k. So I would end up with x minus -4, right, in parentheses, so that's x plus 4 squared, and then plus, and then what I'm going to put in parentheses is this -3, so just -3. So the a value, I haven't really talked about how to figure that out. On this one, it's just 1, and we'll talk about how to figure out that that's 1 soon. But notice I just had to plug the vertex in here and here, and then I see how it moves around. So here we can see another example. Oh, I guess we can't see it until I move the graph, so let me see about moving the graph paper up just so you can see. So here, let me try and cover all of this up and then slide this down just a little bit so we can see. Alright, so we have these 3 graphs. We have the red one, the black one, which is y equals x squared, and then the blue one, which is wider. So the red one, so if it's a parabola, we can kind of figure out the a term. It's a little tricky to kind of figure it out, but we can use this format, and I'll show you, plus k. And since the vertex for all 3, the red, the black, and the blue, are 0, 0, we can plug that in and just see what happens, plus 0. And so we're left with y equals x minus 0 is x, a times x squared for all 3 of them. So a is going to be different even though they're all y equals ax squared. So let's look at the first one, and we'll call that the parent function. How do we know that the coefficient is 1? Well, we can just take any other ordered pair from it. Okay, and so for this one, we can look at the equation 1, 1. We'll use that. So we'll look at y equals x squared, and we'll plug in, okay, we'll use our ordered pair of 1, 1. This is an xy. So if we plug 1, 1 in, we get y equals a times 1 squared. So 1 equals 1a, and if I divide by 1, a equals 1. on the first one, and that's how we get that. Let's look at the red one. So the location of this point right here, it's a little bit hard to see, but it's over 1 up 2, so that would be 1, 2. Now, I could use any point on the curve, but this one is pretty obvious. I could use this one here too, which is negative 1, 2. So I could use either of those, but let's go back and we'll plug it into y equals, we'll look at y equals ax squared and see that it works. We're going to plug in 1, 2, right? So we'll use 1, 2. And of course that is x versus y. So if I plug in 1 and 2, I would have 2 equals a times 1 squared, which is just 1, so 2 equals 1a, or 2 equals a. So the coefficient for the red function would be y equals 2x squared. And that's actually pretty accurate, because if I kind of look at it, the slope change for this is, although you don't want to consider a slope, but it's up 2 over 1, so it's kind of this dilation of 2. We want to be careful calling it slope. It's a dilation, and the effective slope, although yes, there's some relationship to it, it's the slope is what we look for, kind of to find this point of tangency, and anywhere on the curve that slope can be slightly different. But on this curve, let's look at the blue one. How are we going to figure the x squared? Well, let's take any ordered pair. Let's use this one. This is over 1, 2, 3 up 1, 3, comma 1. And so if we do the same thing, if I use 3, 1 as my x, y input output, I have 1 equals a. I'm going to plug in 3 squared, and then what do I get? I get 1 equals 9a, and if I divide by 9, I get 1/9 is the value of a. So on this function, y equals 1/9 a x squared. That 1/9 is the value. And then the last effect is what happens to the graph. So if a is negative, right, so it flips it upside down. So this is a result of a is negative here. So we are flipping it upside down, and so I can put a negative 1 here, although maybe I don't know it's negative 1, but I do, and I'm not going to explain how I know right this second. But this is negative 1, and then the vertex of this graph is 1, 2, so I can plug 1 and 2 here. So I can rewrite this as negative x minus 1 squared plus 2. Now you can check all this stuff on Desmos to kind of verify, but this is kind of a quick introduction to all the characteristics. And if I kind of go back to over here, I now have to kind of talk about, when I looked at the blue curve and the red curve, how the A term affects the dilations in terms of compressions and stretches. So this is only true if A is outside the parentheses. The absolute value of A, when it's greater than 1, we will call it a vertical stretch, because it's kind of stretching this red curve closer and closer to the y-axis, whereas the blue curve, it's compressing it closer and closer to the x-axis, so it's compressing it down. So when the value of A is between 0 and 1, I use absolute value because positive or negative, the curve will be the same. It will just reflect it if it's negative. So look over here, these two curves are the same, so their width is the same. It's just that A was negative. And that's only true if A is on the outside. But this would be what we call a vertical compression. We are squeezing it down. So if I kind of sketched my parent function, right? If I have a function like this that's real soft, it's like I'm pushing down on it, and I'm compressing it down towards the x-axis, versus if I have one that's kind of narrow, it's like I'm pulling it up, so I'm trying to get it to, it's stretching it to the y-axis, and that's kind of the difference. And then of course here, if A is negative, it flips it, which is a reflection over over y-axis, x-axis, because it's a vertical flip. Now, all these things are basically Algebra 1. So where things get a little tricky is that sometimes we overlap a little bit into Algebra 2 with horizontal effects, and so I'm just going to present them right now just so we see them and the difference. So horizontal effects do not happen in this format, which is vertex form. They happen in this format, and they will have some slight nuances of difference. Now notice A is inside here. So because A is inside, our effects will be different here. And when A is greater than 1, the absolute value, this is going to be a horizontal effect because X is the input, which is the horizontal axis, and this immediately affects it. Whereas over here, we had to do some work, then square it, and then we affected the output of that. So that's why we kind of think about this A here affecting the vertical value or the vertical axis, because it does work. It affects after we do the work. So this would be a horizontal compression. And then if A is less than 1 but greater than 0, this would be a horizontal stretch. Now this is kind of a long-winded explanation, but it's a little tricky, and so I would test a lot of this stuff in Desmos just to verify. And then if A is negative in this situation, it reflects horizontally, but that means it's going to reflect across a y-axis, so it reflects across the y-axis, or really kind of across a vertical line, so it's a horizontal reflection. So if we kind of look at this, I don't know if it's a comparison to each other, but I kind of take a look here as we look at the two situations. That we have vertical stretch when A is greater than 1, when A is on the outside. But over here, when A is greater than 1, it's a horizontal compression. And if you kind of think like a horizontal compression, if I kind of think about, like, here's my parent function, a horizontal compression would be like if I was coming from the sides and trying to squeeze this, it would keep squeezing it until it was vertical. So horizontal compression looks a lot like a vertical stretch in the effect, but it's not going to be the same exactly mathematically, so you have to do some calculations to evaluate it, but you can think of similarities in terms of how you can imagine it. So I would test these things on Desmos and practice with some examples.